Let's start with the basics. What exactly is a voltage divider? At its core, a voltage divider is a simple yet powerful circuit made up of two resistors connected in series. Its main job is to take a higher input voltage and scale it down to a lower, more useful output voltage. This is done by tapping into the point between the two resistors and measuring the voltage relative to ground. Beauty of the voltage divider lies in its simplicity. A straightforward ratio of two resistors determines the output. This circuit is a staple in electronics, often used to create reference voltages or to safely scale down signals from a larger supply. Whether you're biasing an amplifier or interfacing with sensors, voltage dividers are everywhere. Now let's talk about the formula that makes voltage dividers tick. The output voltage is calculated using a simple ratio, Vout equals VIN multiplied by the fraction of the bottom resistor over the total resistance. In other words, Vout equals VIN times R2/R1 plus R2. This formula is incredibly handy and pops up everywhere in electronics. It's easy to remember if you think of it as the input voltage scaled by how much of the total resistance is made up by the bottom resistor. This relationship is the key to precise voltage scaling, allowing you to design circuits that deliver exactly the voltage you need for your application. Whether you're working with sensors, amplifiers, or digital interfaces, this formula is your go-to tool. Voltage dividers are more than just a way to split voltage. They're essential for signal scaling, reference generation, and level detection. For example, they're used to convert higher voltages to safe levels for microcontrollers, set bias points in amplifiers, and create thresholds for comparators. In sensor interfaces, voltage dividers can turn resistance changes from devices like LDRs or thermistors into readable voltage signal. To get accurate results, you need to consider factors like resistor ratio accuracy, input impedance of the load, power dissipation, and noise or temperature drift. Thin-film resistors are often chosen for their stability in precision applications. Mastering these details ensures your voltage divider performs reliably in any circuit. Common pitfall with voltage dividers is the loading effect. The classic formula assumes the output isn't connected to anything, but in real circuits it almost always is. When you connect a load like a microcontroller pin in parallel with the bottom resistor, it changes the effective resistance and causes the output voltage to drop, sometimes significantly. This can throw off your carefully calculated values. To fix this, you can use a buffer such as an op-amp voltage follower or make sure the load resistance is much greater than the bottom resistor. These strategies help maintain accuracy and ensure your voltage divider delivers the expected output, even when connected to other circuit elements. To get the most out of your voltage divider, choose resistor values wisely. High-value resistors are great for low-power sensing, while low-value resistors offer fast response and low noise. For precision dividers, use match-tolerance resistors and consider temperature coefficient tracking for stability. Voltage dividers also shine in advanced applications. They're used for op-amp biasing, voltage references in comparators and regulators, impedance scaling in RF circuits, and converting resistance changes from analog sensors into voltage signals. In summary, voltage dividers are simple but fundamental building blocks in both analog and digital systems. Their accuracy depends on resistor ratios, tolerance, and load, making them essential for measurement, scaling, and biasing in countless designs.